Hey, pre-calc students, this is the next day of Unit 4B. We're talking about digging for roots continue today. The whole goal being we know a couple tools at this point to help us find some roots of higher order polynomials. So we definitely know synthetic division, but the trick to synthetic division is that so far I've told you one of the roots. So we want to start finding some other ideas, namely today, the remainder theorem and root location theorems. These might help us start narrowing down our options as far as being able to determine the roots more efficiently of these higher order polynomials. So for this example, x cubed minus 2x squared minus 11x plus 12, I probably should mention that this is in your packet, okay, so you don't have to look for a separate sheet of paper. It starts on page 9, and actually all of today's notes will be in the packet, so that's good news. So what we're going to do is we're going to test to see if any of the following values here are roots: -4, -3, -1, 2, 4, 5. So just lots of synthetic division practice, which is never a bad thing because the more efficient and the better we become at synthetic division, the easier everything else gets later on. So how would I test something like -4? We write the coefficients of the polynomial: 1, -2, -11, and 12. We know we've got to bring down the 1. So 1 times -4 is -4, plus the -2 above it is -6. -6 times -4 is positive 24. 24 plus -11 is 13. And 13 times -4 is -52. And -52 plus 12 is going to be -40. Okay. So we know that in the end, we actually have a couple of things that we're going to conclude here. I know as a conclusion that -4 is not a root of this polynomial. Definitely didn't get a remainder of 0. So the conclusion is -4, definitely not a root. One other conclusion, though, that maybe we haven't quite gotten to yet is that this value right here is going to correspond with something specific, that remainder. It will help us know something about a coordinate point on the graph. And maybe we'll wait a second to fill that part in because we're going to learn something on the next page that will help us with that. But what I would like you to do at this point is I would recommend hitting pause and making sure that you are really solid with the rest of the synthetic division to test these other roots, right? So to test -3, you would rewrite those coefficients: 1, -2, -11, and 12. Bring down the 1 and just start that process all over again. Okay, so try the rest of those roots. I'm going to show you what my results are. And then hopefully in the end, you'll find that some of them are roots because some of them will work out. And then we'll take that information and start building a sketch from there. Okay. So let's take a look at the answers. Hopefully you hit pause at this point. -3 turned out to be a root. And again, the reason why I know that is that the remainder there is 0. -1 turned out not to be a root. We had a remainder of 20 when we tested -1. So by the way, beyond determining yes or no for a root, zeros are pretty important. The value of the remainder is going to be pretty important for us when we're talking about something called the remainder theorem and actually root location theorem as well. So make sure that you have the correct remainders, even if it's non-zero. Typically we don't, it wouldn't matter too much, but the value of the remainder is important. Okay, so when we test 2, you should get a remainder of -10, indicating that 2 is not a root. X equals 4 gives you a remainder of 0. So that means that 4 is in fact a root. And then finally for x equals 5, we get that the remainder 32. So 5 is not a root in that instance. So what we can do with this information is we can start building a graph of what this looks like. So if I come back down to where it says graph each of the coordinates, the 2 main coordinates that we know at this point are really just the locations of the roots. So we know that we have a root at -3 and also at +4. And since this is a cubic polynomial, we know that we have to have one more root somewhere. Okay, we need a total of 3 roots. We have one at -3, one at 4. So it's going to cross the x-axis again at some location. I'm not exactly sure which location yet. But if we turn the page, we're going to find some things that will help us to make this determination. Okay. So the polynomial we were just looking at, by the way, was x cubed minus 2x squared minus 11x plus 12. That's how p of x was defined on the first page. And it says, since polynomials are continuous over the real numbers, let's take a closer look at these two values, p of -1 and then p of 2. So to calculate p of -1, it's hopefully exactly what you're thinking here. Just plug in -1 for x in all those locations. Okay, and let's see, when I do that, this is -1, this is +1, so 1 minus 2 is -1, and then plus 11 is going to be 10, and then plus 12. Hold on, am I doing this wrong? -1 cubed is -1. That's 1 minus 2 is -1. -1 plus 11 is 10 plus 12. Is that 22? It's not the number I had written down. Oh boy, guys. I better check this on the calculator. I don't know. All right, good thing we have a calculator here. So, -1 cubed. Am I thinking about this wrong? My brain isn't working tonight. All right. Minus 11 times -1. And then with the plus 12 at the end. Yeah, the answer is 20. What was I doing wrong? So that's -1. This is +1. Oh, -1 minus 2 is -3. -3 plus 11 is 8 plus 12 is 20. Okay. Boy, wish somebody was here to stop me with that one. Okay, we'll call that a 0 there for 20. Oof, I hope 2 is easier. 2 cubed minus 2 times 2 squared minus 11 times 2 plus 12. All right, so this is 8. 2 squared is 4. So now it becomes -8. So those cancel out, 8 minus 8. So we get -22 plus 12, and that's -10. Okay, I'm pretty confident about that one. So here's what I want you to think about. When you input a value of x of -1 and the output is 20, that's a point on the graph. That's an xy coordinate point. -1, comma 20, let's say, is this point right up here. When I plug in x equals 2 and the output is -10, that's another point on the graph. Well, in order to get from the point -120 to the point 2 comma -10, don't we have to do this special thing called cross the x-axis? Hence, there will be a root somewhere in between. So this is what's known as the root location theorem. Okay, it's a really fancy name for when we see this sign change, when we go from a positive output down to a negative output for y, we know that we're going to have to cross the y value at 0, which is where we're having x-intercepts. So since we notice that sign change happening, the function must cross the x-axis between -1 and 2. So we're going to make a really good guess for x equals 1 and see if that happens to be a root. So if we go back and test x equals 1, with the coefficients 1, -2, -11, and 12. Okay, we can bring down that 1. 1 times 1 is 1, plus the -2 above it's -1, times 1 is -1, plus -11 is -12, times the 1 is -12, plus 12 is 0. So 1 is in fact a root. It wasn't in the original list from the front for us to check. So if I wanted to go back and think of making more of a complete sketch here, we also know that x equals 1 happens to be a root. Now, one quick note about this is that all of these other remainders that are non-zeros, those wind up representing coordinate points as well. So didn't we just do p of -1 and we got that the answer to that was 20? You can also use synthetic division to confirm that the point -120 is on the graph. And we also just showed that p of 2 was -10. Look how we get that same result from synthetic division, that when you test 2 with synthetic division, the remainder is really the y value that we're getting there. So if I were to come down to the graph here, I could have plotted the point -120 and the point +2, -10, and use those as values to decide, hey, you know what? To get from this point up here down to this point over here at 2, -10, we're going to have to cross the x-axis in order to make that happen. And it just so happens that a good point to choose between -1 and 2 for now is x equals 1. Seems like a nice value to test. Did it have to be x equals 1? No, it could have been a half. It could have been, really anything in between -1 and 2. but x equals 1 happens to be a nice, easy number for us to test, and luckily in this case, it worked out for us. So just know that when you're doing synthetic division, even though we're not always getting roots, the remainders tell us something nice. This is the 0.5, 32 on the graph, if I wanted to make an overall complete sketch of what this graph looks like. Okay, let's go to the next set of examples where it says, let's find f of 1 here using 2 different methods. Okay, so to find f of 1, you can do one of 2 things. You can just plug it in to the function. That's, I feel like, what our go-to would be. But what we just saw is that you get the same result from using synthetic division as well. That the remainder in synthetic division is the y value that you're getting when you do f of 1. So f of 1, let's just do that real quick. In this function, it would be 7 times 1 to the 5th minus 2 plus 3 times 1. So in this case, we're going to get 7 times 1 to the 5th. 7 times 1 is 7 minus 2 plus 3. 7 minus 2 is 5, and 5 plus 3 is 8. Okay, so f of 1 is definitely 8. Could we also convert that using synthetic division? I hope so. So here's the thing. If we want to find f of 1, 1 is the root that we're testing. And when we go to write the coefficients, what I'm hoping you're thinking about here is that synthetic division would actually be really annoying to use here to find f of 1. And why is it really annoying? It's because the coefficient of x to the 5th is 7, but then we're missing x to the 4th. So we need zeros for all those placeholders. There's x to the 4th, x cubed, x squared. You need a 0 for each of those placeholders. 3 is the coefficient of the x term. Oh, and by the way, the coefficients are out of order too. So you got to make sure you pay attention to that. And then -2 is the constant at the end. So bring down the 7. 7 times 1 is 7, plus 0 is 7. 7 times 1 is 7, plus 0 is 7, and you kind of get those 7s to pop up for a while. And then towards the end, add the 7 and the 3 to get 10. 10 times 1 is 10, plus -2 is 8. So we can confirm that 8 is in fact the remainder with synthetic division, testing x equals 1. 2 different ways to generate that f of 1 in the end is equal to 8. So there are benefits to this idea over here, and this right here is known as remainder theorem. Remainder theorem essentially just says that when you plug in this value for x in the function, the y value, the output, is the same thing as the remainder when testing that value in synthetic division. And that becomes pretty helpful in knowing that, this is a concept right here. When one remainder and one output there for y is positive, and then we go to a negative output over here, we know that we're definitely crossing the x-axis. It may not seem like an exciting idea right now, guys, but I promise that when we start doing tougher cases where we're trying to find all the roots, this is something we're going to think about a lot. Okay, let's try this example here. H of x is 2x cubed plus x squared minus 13x plus 6. First question is 0 a root. Let's test it out. 0. So the coefficients are 2, 1, -13, and 6. So bring down the 2. 2 times 0 is 0, plus the 1 above it is a 1. Times 0 is 0, plus -13 is -13. Then we get a 0 again, right? And then plus 6 is 6. So 0 root? No. Not a remainder of 0, remainder of 6. And we're probably not even that surprised that we actually got that same set of coefficients again. That will be something that we use later on too. All right, how about 1? 2, 1, -13, and 6. Is that a root? Bring down the 2. So 2 times 1 is 2, plus 1 is 3. 3 times 1 is 3, plus -13 is going to be -10 times 1 is -10, plus the 6 is -4. So this is also a no. So why did I have us just test those two if they're both no's? Well, what I want you to look at is the remainders. We went from a remainder of 6 to a remainder of -4. And if we think about what that implies about the function, this corresponds with the point 0, 6 on the graph. It's actually the y-intercept, right? And then this corresponds with the point 1, -4 on the graph. So in order to get from 0, 6 to 1, -4, guess what I have to do? I have to cross the x-axis somewhere in between those values of x equals 0 and x equals 1. So what should our next guess be? Well, there's a lot of values between 0 and 1. to make our lives easy, why don't we choose the halfway point? Let's choose x equals a half. Hopefully that works. If not, we might be able to narrow down our guess even a little bit more. Okay, so for example, if I got a negative remainder for 1/2, then I know that the root is somewhere between 0 and a half. So I can maybe narrow it down from there. Well, let's try what happens with 1/2 as our next guess. Bring down the 2. Half of 2 is 1, plus the 1 above it is 2. Half of 2 is 1 again, plus -13 is -12. Half of -12 is -6, plus 6 is 0 to save the day. So x equals 1/2 is a root of this polynomial. And there'll be other tests that we find later on that will help us, again, narrow maybe even down our guesses as to what fractional roots would make sense to test. Luckily, in this case, 1/2 did wind up working out. And we shouldn't be too afraid to test fractions, especially something like a half. That one wasn't so scary. Okay, we've got 2 left to take a look at. We're going to show how do we test complex roots. And this is kind of a weird concept. But using synthetic division with a root like 3 minus I to see if it's a root, the way we're going to do this is we're going to put 3 minus I as the root in the box there that we're going to check. And the coefficients of it's only quadratic, which is nice. So there's only 3 coefficients I have to write down, the 1, the 5, and the -3. If it was cubic, we'd have 4 coefficients to write down, but we're going to bring down the 1. 1 times 3 minus I is 3 minus I. It's just a little weird because now we have to add these complex numbers together. Well, the 5 plus the 3 is 8, and carry down the minus I, right? This doesn't have an imaginary part to it, but we would have 8 minus I if we added those together. And the only weird thing now is to multiply 8 minus I times 3 minus I. That's what goes in this spot right here. So for those of you that love box method, maybe I'll do it for this one. I'll do FOIL for the next one. Okay, so 8 minus I times 3 minus I, this is 24, -3I, -8I, and positive I squared. So that's going to be 24 minus 11I plus I squared. Don't forget, we know what I squared is. I squared is -1. So 24 plus that -1 is 23 minus 11I, and it's definitely looking like when I add those, I'm not going to get 0 as a result. What is the remainder here? It's 20 minus 11I. So with that remainder, we can confidently say that no, 3 minus I is not a root of this polynomial. Okay. I'm going to give you a spoiler alert for number 2. I want you to try it, but where it says, is 1 minus 2I a root? I'm going to tell you the answer is yes. So see if you can actually confirm that 1 minus 2I is a root, but I'm going to do it real fast. Okay, let's see if we get the same answers. 1, -2, and 5 are the coefficients. Bring down the 1 times 1 minus 2I. Add it to the -2, so now it's a -1 minus 2I. All right, so when I do -1 minus 2I times 1 minus 2I, what happens? Okay, so we're going to get, if I do FOIL this time instead of box method, -1 plus 2I minus 2I, and at the end that's going to be plus 4I squared. Well, 2I and -2I cancel. Oh yeah, and I squared is -1. So 4 times -1 is -4, which is a total of -5. And as soon as I know that that's -5, we like that because -5 plus 5 is 0. So a little bit odd when you're testing complex roots, but I believe there is something like this in the textbook homework. So you'll see that in our next assignment. Let me know if you have any questions about that, but we've learned a few more tools today, and actually this is only just the beginning, guys. A lot more tools coming your way. Have a great day.